the empirical rule stated that if your data is bell-shaped and symmetric, okay, and the actuality is that it just has to be somewhat normal, okay, and that's the word that we're going to use eventually to refer to bell-shaped, okay, meaning that we don't want, if we go back to the skewness, we don't want things like this one here on the left or this one here on the right. We're looking for something like this, okay? Now it can be off a little bit and we can still kind of still hit these approximations with our, or the thresholds that are existing inside these percentiles for the empirical rule. Basically what it says is if we have a list of data and it's bell-shaped, then 68% of our data is going to be within one standard deviation of the mean. So what does that mean to us? So what I've done in your email, you don't have to open it now, but you can mess around with this. But I sent you one this morning that had an empirical rule, like Excel sheet on it. And it should look like this, okay? And basically what this is allowing us to take 50 pieces of data, okay? Whatever they made, they were randomly generated by actually this sheet right here, okay? And I just cut and paste them into these individual sheets. But what it's going to allow us to do is determine what the standard deviation and what the mean are, and then count how many of those data points are actually inside that one standard deviation range, okay? So I think it'll make more sense here if we just kind of plug away and get this mean and standard deviation figured out, okay? So if you remember back to what we did the last couple of days, we were doing standard deviation by hand, right? And that's a nightmare to do, especially if I got 50 pieces of data. So we've got a nice ability here. If I want to find the mean, obviously I'm going to hit equals and then type in average. And then I want to go, I've got 50 pieces here of data, so I'm going to go A1 to A50. Hit enter, and I've got my mean, okay? We can then go down here and standard deviation. This is where the formula got kind of nasty, but I can type in STDEV, okay? And it gives you this list of options here. Now, I'm going to go from I'm going to say that these 50 are from a sample, okay? So I'm going to hit .s for sample. And then all I've got to do is type in the list of data that is my sample. Yes? You good? Okay. So I got my standard deviation, okay? So this tells me how spread out my data is, okay? And we can actually then start to look at specifically how spread out it is. Meaning, if I take my bell curve, my normal curve, which looks like it's pretty laggy. Man. All right, so I take my bell curve, okay, and I know that's not the greatest picture. But our mean, median, and mode should be right there, correct? Okay, so I'm just going to say X bar, okay? Now, if I take and add one standard deviation that direction, okay, I should get there, so that would be X bar on my X-axis, that'd be X bar plus one standard deviation. If I go this direction, it will create that position on my X-axis, which is X bar minus one standard deviation. And what we find out is, based on the empirical rule, it'll all color in here in a minute. Based on the empirical rule, 68% of these numbers over here in yellow are going to fall in between that line there and that line there. So if we were to go in and actually make like a dot plot here and say, okay, well, 52, where should 52 be? Well, my mean is 39 right now, so right there is 39. 52 would be maybe like right there. Does that make sense? Okay, and I go find 60. Well, 60 might be there. And if I keep doing this, most of my data, 68% of these numbers over here, are going to fall in between that spot and that spot on my bell curve. Does that make sense? Okay, so I want you guys to see that and have that justified to us. So this position right here would be my mean plus 1 standard deviation. So I'm going to go to this cell here, and I'm going to say equals my mean, which was in C1, plus my standard deviation, which was in C2. Okay, so this position right there is 49.8. And then I'm going to find this position over here, which is my mean minus my standard deviation. So this is going to be C2 minus or C1 minus C2. It gives me 29.07. So between 29.07 and 49.8, I should have 68% of these values falling in there. Okay. Now what we could do is we could actually go through. Okay, will that number fall in that range? No. Will that one? No. Will that one? Yes. Okay. And we could say, okay, so that's 1. And then, will that one? No. Will that one? Yes. So I can go through and count them, right? Okay. And then take that amount and divide it by 50. But I've created a formula over here. I'm not going to get into asking you guys to actually write these formulas, but what this does is it says it's going to search through all of my A column, and I go all the way to 1,000. And it's going to say, look for numbers that are bigger than C3. Well, C3 is this one here, right? So look for numbers that are bigger than 29. And then look through A1 through A1000, and look for numbers that are smaller than C4. Well, C4 is this. So what it's going to do is it's going to search through this column and start counting if the numbers are between that number and that number. Does that make sense? So when I turn it into a formula, by putting equals in front, it'll actually do that, and I get 33. Okay? Now I'm going to take, so n was 50, right? We got 50 terms over here. Okay? If I take that number divided by that number, I get 66%. Okay? So 60% of these specific values right now would fall in this orange. Is that approximately 68? That kind of makes sense. It's in the ballpark, right? Now, the more data points we have, the better that 66 will become closer and closer to 68. But let's look at it for 95. So 95 would be the same idea, but I'm going to now search off of these two, okay, which I've got to put those in as well. So the mean minus 2 standard deviations. So my mean is C1, and I'll minus then 2 times my standard deviation, which was found in C2. And then in the second one, it will be my mean, which is C1, and I'll add to it 2 standard deviations, which is C2. So now you see that it makes that range of values greater than what it was here, right? So now we're going out to, we're going to add 1 more standard deviation. Oh man, went too far. So that distance there is 2 standard deviations to the left, and over here would be 2 standard deviations to the right. So we're looking now at how many data points should fall in that green region. Well, it should be 95%. That's what the empirical rule says. So if I take and change this formula into an executable formula, we get 49. Okay, well, I'm going to take then equals that number divided by 50. It gives me 98, okay, which is in the ballpark of the 95% that we're looking for. Does that kind of make sense? Now, we could do this, and my plan was to show you doing this with 100, doing it with 200. So each one of these sheets here, we can go in and fix our rules for our mean, standard deviation, and so forth, and do that. But what I want to do is I'm just going to real quick, instead of running through all of those with you, I'm just going to generate another random list here. Okay, so when I do that, creates this list here. We'll pull off those, come back here. So 52 and 60 were the first two there. I'm just going to paste here, and you see 38 and 25 now, so it's a completely different list, right? Okay. Now it automatically went ahead and calculated the mean, standard deviation, all that kind of stuff, these upper and lower bounds, and you see we're in the ballpark, around 68, around 95. Okay. And the reason it's not necessarily 68% and not necessarily 95% is that this data, the way it was developed, is not 100% normal distribution. Does that make sense? Okay, but it's slightly normal. Let's do this. Let's go ahead and I'm going to change this to 1,000, and we'll generate a list of 1,000. Okay, so I'm going to paste those values in. So I've got a list of 1,000 here. Okay, N is 1,000. Okay, we see that when we do this count here, okay, 663 of these values fell between those two numbers. Well, 663 divided by 1,000, 66.3%, pretty close to 68%, right? Look how close this is to 95%, 0.95. All right, so that's the idea of working with the empirical rule. And we can go even further. We go 99.7 if we want to go within 3 standard deviations. Okay. What I want you guys to know, I want you to realize is one of the key features that's going to be beneficial for us throughout the rest of this course. Because in the next chapter, we're going to start talking about probability. And there's a direct link and usage of the empirical rule with probability. A lot of our statistics are based off of probability, and we have to use the empirical rule to make conclusions of or about our probability. Does that kind of make sense? Okay. So that image, that understanding of that bell curve and that 68%, 95%, 99.7% is going to be something that is going to stick around. Okay. When we talk about bell shape or normal distribution, sometimes they call them Gaussian probabilities or Gaussian distributions. Gauss was a famous mathematician. Did a lot of linear algebra stuff. Okay. Yesterday when class ended, I wanted to start talking about what we call z-scores, okay, or standard scores, okay. I'm going to skip through this explanation right here. I'll let you guys read that on your own, okay. But what a z-score is basically taking, and I think we talked about Lucas yesterday, we talked about heights of everybody, okay. If I took everybody's height and we found that it was normally distributed, and we found the standard deviation and the mean and all that kind of stuff. And we found that, how can I take Lucas's height and now compare it to everybody else or compare it to the mean? We would want to know how many standard deviations away from the mean is his height, okay? If we go back to this, okay, I would want to know if I look at this 34 here, okay, how many standard deviations away from the mean is my 34? And it's not very much, right? It'd be a very small number because my 34 is very close to my mean, okay? This number here would have a greater standard deviation away from my mean. Does that make sense, everybody? So basically the z-score or standard score is going to allow us to determine how far away individual particular values in our data set are away from the mean, okay? And that will allow us then to compare things from different populations, which is beneficial, okay? So finding a z-score, we're going to use, to save time here a little bit, we're going to use these two formulas, okay? The formulas in the middle are how these are generated, okay? Basically it says your data point is equal to the mean plus your z-score times your standard deviation. Well, if I solve that for z, I will get this formula right here in yellow, okay? They're the same formula. One is talking about the sample, one's talking about the population. So remember, in a sample, x bar is the mean. In a population, mu is the mean. In a sample, s is the standard deviation. And sigma in a population is the standard deviation, okay? But kind of talk about what this means. And this is where you're going to see a lot of our questions. They're making the assumption now that you know how to find standard deviation. So when they go to a new type of question, they don't give you all the raw data. They will have already processed that raw data, and they will tell you, of the raw data, we now have a mean, and we have standard deviation. Can you now tell the location or and its relative location of how well somebody that took this LSAT and took the MCAT did in those tests, okay? So if you read the scenario, it says before applying to law school in the U.S., students need to take the LSAT. It says before applying to medical school, they need to take the MCAT, okay? It says here are the summary statistics for each exam. So those exams are two different populations of people, right? Okay. So if there's a mean of 151 and a standard deviation of 10, one, that test is different. It's graded different than what the MCAT is or any other test that we take. Okay, but if I took both of them, I want to know based on my score, how did I do in comparison to the people that took that test? Which one did I really do better relatively comparable to the people that also took that test? Does that make sense? Okay. So what we do is we find the z-score of these two things. So if I find the z-score of the LSAT, okay, it is, now we've got all of the people that took this. So we're talking about a population. So it's going to be x minus mu over your standard deviation sigma. So my particular score on the LSAT, or this person, Juwan's score, was 172. So we go 172 minus the mean, which was 151, divided then by the standard deviation. Okay, so that gives me, what, 21 over 10, which is equal to 2.1. That was my z-score. Does that make sense, everybody? Okay, so if that's the only thing that I was interested in, what that tells me is if I'm looking at these scores as being normally distributed, the median right there is the same as the mean, which is the same as the mode, and it's 151, right? What would tell me is if I go two standard deviations that direction, okay, which would be 171, right? We got a 172, right? We were just to the right of that, okay? If you are beyond two standard deviations away from the mean, we refer to that as an unusual data value, okay? And I'm talking about my performance on a test, and I did unusual, and I'm above the mean. That means I scored better than most people that took that test, right? Does that kind of make sense? Okay, I have a rare outcome because of how well I've done on it. Does that make sense, everybody? Okay. Now, if you were 2 units to the left, this number would be negative. Does that make sense? 2 standard deviations to the left, and it would be negative. So the positive or negative aspect of a z-score tells you the direction you are from the mean. So if I do the MCAT, we're looking at, again, x minus mu over standard deviation. But x in this case is 37. Okay, the mean was 25.1. So you see right there with these data, I mean, the tests were scored completely different, right? One's out of, has a mean of up in the 151. The one has a mean of 25.1, okay? So they're drastically evaluated differently, but if I go ahead and do that algebra, 37 minus 25.1, and then we'll divide that by 6.4. I get a z-score here of 1.859. Okay. Now, what does that tell me? Well, that tells me I'm 1.859 standard deviations above the mean for the MCAT, right? But what is real nice now is that I can tell which, in comparison to the people that took the LSAT, in comparison to the people that took the MCAT, which group did I do better in? Which test did I do better on, relatively speaking? I did better on the LSAT, right? Because it's a 2.1 greater than a 1.8. Okay? And that allows us to make judgments, make arguments or comparisons of essentially two scores or two data points that are coming from different populations. Okay? Couple other examples here. I want to jump down to an example. It's not in your notes, and I got it printed off, so I'll give it to you in a minute. But it is... here. Huh? Rest in peace. Where? Oh, yeah. Yes. Formulas are going to be given to you. But the 68%, 95%, that kind of stuff is going to be on you. All right, so got an example here, a couple examples of Z-scores. First one says, in 2009, Heath Ledger won the Oscar for Best Supporting Actor at age 29 for his role in the movie The Dark Knight. Penelope Cruz won the Oscar for Best Supporting Actress at age 34 for her role in Vicky Cristina Barcelona. It says the mean age of all Best Supporting Actor winners is 49.5, with a standard deviation of 13.8. The mean age of Best Supporting Actresses is 39.9, standard deviation of 14.0. It says find the Z-scores that correspond to the age of Ledger and Cruz and then compare results. So what we're asking here is, okay, he won it when he was 29 years old. Is that, and because the average age is 49.5, so he won it 20 years younger than what the average age was, right? Our question is that unusual? Statistically speaking, is that an anomaly? Does that make sense? Okay. So if I want to find the Z-score of Heath Ledger, okay, and I always like to put subscripts for, especially if I'm finding multiple Z-scores, so just subscripts that remind me what did that Z-score attach to. Now I'm talking about Oscar winners, and I have all of the data from everybody that's won an Oscar for Best Supporting Actor or Actress. So we're talking about a population here. So it's X minus mu divided by the standard deviation. So X, remember, is your particular data point. So in this case, Heath Ledger was 29 years old. Minus mu, which is our mean, and that's 49.5. And we'll divide by our standard deviation, which is 13.8. Now I'm gonna go ahead and do Penelope Cruz as well. At the same time, then grab my calculator and do them both. So she won it when she was 34. So that's X. The mean for actresses was 39.9. And the standard deviation there was 14. So calculating those two things then, 29 minus 49.5, 20.5 divided by 13.8. This gives me 1.48551. Okay, and it's negative, and we'll talk later about the precision that we should go to, like decimal place wise. And this is negative 0.421429. Okay, so relatively speaking, okay, compared to the groups that they came from, the populations that they came from, Heath Ledger was much younger than anybody else that won the Oscar, right? Okay, he was much younger compared to his group than what Penelope Cruz was compared to her group, right? He's 1.48 standard deviations below the mean. So he's 1.4 standard deviations essentially younger than the mean. Does that make sense? She's only 0.4 younger, okay? Now, neither of them are over 2 standard deviations, right? Okay, when we talk about 2 standard deviations, we're talking about either above the mean or below the mean, okay? Neither of them are in those positions, so neither of those would be considered statistically an anomaly or an outlier, unusual, okay? Even though, 20 years, he's pretty young, there were people that are younger that won it as an Oscar. Is that okay? Does that make sense? Okay. I gave the first class, because we ran out of time because we were messing with the projector and trying to get that fixed. I gave them these next 2 for homework. Okay, so do you guys want to do them now or you want to do them for homework? Want to do them now? Let's jump, since this one here is really the same scenario, it's just talking about 2 different actors. So let's skip that one. And if we don't get that one done, you can do that one for homework. But let's come down here to the one with the fruit flies. So the lifespan of a species of fruit fly have a bell-shaped distribution. It says with a mean of 33 days and a standard deviation of 4 days. So the lifespan of 3 randomly selected fruit flies are 34, 30, and 42. Find the z-scores that corresponds to each lifespan and determine if any of these spans are unusual. Okay. So I'm going to write z-score. I'm going to put just a subscript of 34, one of 30, and then one of 42, just so I can remember which one's which. All right, so now I'm talking about, it says the lifespan of a species of fruit fly have a bell-shaped distribution. When I look at these 3 fruit flies, do I know the population? Or am I talking probably about a sample here? Yeah, so if I'm talking about population of fruit flies, that's every fruit fly, right? And I can't gain my standard deviation and my mean from every single fruit fly. So what we're talking about here is most likely x minus x bar over s. That's going to be the formula used for a z-score here. It's still your data point minus the mean divided by standard deviation. So then our particular fruit fly was 34, minus the mean, which we said the mean was 33 days, with a standard deviation then of 4. So it gives me, what, 0.25? Then the next one was 30 days. So again, it's x minus x bar over s. So we'll go 30 minus 33 divided by 4. So that's going to give me negative 0.75, right? Gives me 3/4. And then this 42 is going to be x minus x bar over s. So 42 minus 33 all over 4. So that gives me what, negative 9/4. Oh, I'm sorry. You're right. Positive. My fault. So 42 minus 33 gives me 9. 9 divided by 4 is 2.25. Okay, so now here's my question. Are any of these unusual? Last one's usual, right? Or unusual. Meaning it lived longer than what most fruit flies in the population lived, right? Okay. You guys see, like every once in a while in the news, they'll talk about like the oldest person in the world just passed away or something like that, okay? And if we compare that oldest person in the world to like the world population, then they're unusual, okay? But a lot of those people are of like Japanese or Korean descent, and if we compare them to those populations, maybe they're not unusual. Does that kind of make sense? Okay. And how would we determine that? How would we determine, are they unusual compared to the world population, or are they unusual compared to maybe their same background or same ethnicity or same culture. How do we determine that? We could use z-scores to make that argument. Okay, so z-scores allow us to compare data values from two different populations. That okay? My hope is that obviously that formula is not difficult, right? The algebra is not hard there. It's the understanding of what the numbers mean that is important for us in the statistics. Okay? And that's something that through statistics is going to be commonplace, where either we do very short computations or we use a program to do it, and then we analyze the number. Okay, and we have to have that understanding of what that number is telling us and how we can use it to make comparisons or predictions or inferences about something else.